Getting set up for some experiments today. How you doing there, two-timer? Yeah, we got some experiments ready for us today. Let me get everything all set up here. Oh, great. Hello there, Just Richie. Welcome aboard. Just trying to get everything ready to roll, baby. Ready to roll. Here we go. Let's fill this flask over here on the left with a little bit of water. Actually, it's going to take quite a bit of water. It's on a magnetic stir plate. So there's a little magnetic stirrer in the container that's being powered by a magnet in the stirrer. And that should cause it to spin. And that's going to cause a liquid to spin. I think that's going to look a little nicer if we top that off a bit. What do you think? Hello there, two-timer. Here we go. Let's put a little more in there. Let's have a good time today. All right. What's next? Universal indicator, baby. We got to get the universal indicator going. What is universal indicator? Well, it's an acid-base indicator. It's going to tell us the pH of something, how acidic or basic it is. Let me zoom in on this just a tad. There we go. All right, let's get some universal indicator in here. The universal indicator, you'll notice, has a green color to it. There we go. It's that beautiful green color. We'll put it into the water. And that's water from my tap, which is just a little bit basic. It mostly looks neutral. There we go, and it goes. Oh yeah, we're making a vortex. You can see some interesting flow patterns going on. But you'll notice mostly the material that I add stays focused in the center of the vortex. That's because that center of that vortex is low pressure. And material, you know, if it's in a low pressure region, it tends to stay there. Material moves from from high to low pressure. So if it's already in the low pressure region, it's going to tend to stay there. I think that color's looking kind of nice. What do you think? Let's try just a bit more. Just a bit more. There we go. Okay. Now we're going to add either acid or base. So here are the different colors that universal indicator can display depending upon pH. Let me show you those here real quick. Actually, they're right here. Those are your different colors that universal indicator will display with pH. So you can see it's like a neutral color now. It's like a green color. We're going to add either acid or base. So let's start off by adding, let's add some acid, shall we? So I'm going to add like 2-3 drops of acid. There's 1, 2, 3 drops of acid. There you go, man. Just enjoy the color show, huh? What's our pH going to end up at? Looks like a pH of about 6. So a pH of 6 is going to be a yellow color according to our indicator. Let me add a few more drops. 1, 2, 3, 4 more drops. You see where I add the acid, it turns red right away. You know, acid's a low pH, and so it's going to turn my universal indicator a red color. But as the mixture homogenizes, we might see that settle into maybe an orange color. So that's going to be a pH of like 4, maybe 5. Let's add a few more drops of acid. Here we go. Actually, it's pretty much turned back to yellow, didn't it? Here we go. 1, 2, 3, 4, 5, 6 drops of acid. Get that nice fire red color. We're down to pH 3. Yeah, I think so. pH 3 or lower. So here's the different colors that you're going to see at different pH values. Actually, that's got something in the back. Let me get a little better pH key for you to see. We'll use this one right here. This particular color right here. We got to cut it out here just a second. We put it down there at the bottom. You can see all the different pH colors. There we go. There we go. So yeah, those are different colors that you'll see at different pH values right there. Right there. Okay, now what we're going to do is we're going to add some base to this. All right? So adding a little bit of base to our mixture, and let's see what happens. Let's just change the lighting just a bit so we can see this nice. There we go, baby. All right, let's add some sodium hydroxide base. Cut this light off, and let's get to work. Here we go, baby. Hello there, school, Halloween. Welcome aboard. Here we go. Welcome aboard, Michael. Let's go like 2 drops of base. 1, 2. And let's see what happens. Come on, man. A little flash of the rainbow. Oh, LJ. That was a little rough when I put bleach in, man. Yep. We might do that again today. So, yeah, here's the different colors that will be displayed at different pH values. You can see right there in the middle, that nice purple color. That's where I added the base. We're up to like pH 10 there, where it's quite basic. And it looks like the system has relaxed to about a pH of around 6, roughly pH 6. Maybe I'll put that right down there at the bottom. We just slide this back just a bit so we can see all the different colors there. There we go. All right, so you can see that pH key down there at the bottom. And now let's start adding some acid back to this system. I'm going to go 2 drops, 1, 2 drops of acid. You can see when the acid hits, it's going to change it to like a pH of 3. But, you know, the acid and base that's contained in there will react with each other. It looks like it's going to settle in at maybe a pH of 4, maybe 5. I'm going to continue to add the acid. The acid I'm adding, by the way, is hydrochloric acid. That's the same acid that's found in your stomach. It's just a lot more concentrated than the acid that's found in your stomach. Like 100 to 1,000 times more concentrated. Yeah, we've got a nice red color. It's not battery acid, school Halloween. That's sulfuric acid. The acid that I'm adding is hydrochloric acid. 20% by weight hydrochloric acid. I'm going to add just 1 more drop of it just for good measure. And now we're going to start adding base. So the base I'm going to add is sodium hydroxide. Here we go. A drop of sodium hydroxide base, and it goes. You can see it turns it violet. And there's all sorts of stuff going on as the system tries to equilibrate. You can see the violet color there in the middle, where most of the base stays, but it does end up moving out along the sides. Let's add another drop of base here. And that pH is slowly going to rise. We went from a pH of 6. Looks like we're at a pH of 7 or 8 right now, yeah. What's nice about this particular container is it takes a little while for the system to... Oh, you said add battery acid. My fault, school Halloween. That's on me. I'm going to turn this down a little bit. It looks like we're neutral, right? We've neutralized the system. Actually, it looks like it's relaxed back to maybe just below pH 7. Is there a way to make hydrochloric acid from water and table salt? You can make it from table salt. What you would do to make it from table salt, I'm going to add another drop of base here while I'm talking. There it goes. To make it from table salt, what you would do is pour battery acid, sulfuric acid, on table salt. If you do that, it makes a gas. And the gas that's made is indeed HCl gas. So I've done that reaction. It's a little wild to, be pouring, something onto salt and you're making a gas. It does look that magical, doesn't it? They're done. And we're around pH 8. You can see the pH scale down here. It's a little bit obscured by the comments, but it's right here. We're about pH 8. Okay. And I am going to continue to add base. We're going to see what happens as the base I'm adding, by the way, is sodium hydroxide. Sodium hydroxide base. Add a little bit more. Here we go. Another drop of sodium hydroxide base. We'll do this experiment over here maybe when we get like 100 people in the live. All right. We'll switch over and do this particular experiment. There we go. We got up to pH 10. All right. So now I'm going to start adding acid. We can watch what happens when I add acid. Here we go. A drop of acid. 1 drop of hydrochloric acid. Doesn't look like a whole lot happening there, does it? Let's add another one. Here we go. Another drop of hydrochloric acid. Oh boy, another drop of hydrochloric acid. Thanks for everyone who's liking the live. I appreciate that. I see those hearts coming through. Just barely see some red there. Just a bit. Let's add another. Oh, there we go. We see a slight color shift. Let's add another drop of the acid. Hydrochloric acid is what I'm adding. The same acid's found in your stomach. There we go, baby. Come on now. Let's add 3 more drops. There we go. It's like the day breaking through the night. Kind of interesting, huh? Let's get this sped up. Let's get this baby sped up. Come on, man. I want to see this go. Get that vortex centered. Let's get going here. Let's add a few more drops of acid. 2, 3. Hello there, Don Pelton. Thanks there, Don. Appreciate it. Oh, I won't be drinking it there, Biz. I'm not going to drink it. One of the dyes that's present in the indicator used to be the active ingredient in X-Lax. So that might, end the live in 10 or 15 minutes. Here we go. We're down to like a pH 3. See that nice red color? Give me a thumbs up if you can actually see this key when I hold it down here at the bottom of the flask. And give me a thumbs down if it's a little too hard to see because of the comments. I guess I can just alter it just a bit. We can do just that. There, it's right there at the top of the comments. Here we go. Looks like we're at like pH 4 or 5. It's orange. I'm going to add another drop of hydrochloric acid. 1, 2 drops. Okay, folks can see it. That's good to know. That's good to know. Appreciate that down in school Halloween. Good to know. All right, let's start adding some base. Come on now, 1 drop. Let's see what happens. Let's see if we get the rainbow. Here we go. 1 drop. Boom. In it goes. There it is, baby. Come on, man. Yeah, we got a little flash of the rainbow there for a second. All right, pink axolotl. Pink axolotl wants some purple. That's what we're going to go for. I've added some base to the acid. You can see we're up to like pH 4, 5, maybe 6. So as I add base, it neutralizes the acid. There's another drop of base I've just added. You can see the violet color grow into the vortex. And as it reacts with the acid, let's see if it neutralizes it. If this if this relaxes to a green color, that means the acid and the base that are present in the system are completely balanced. We're going to get there, pink axolotl. See that green color? Of course, it's not completely homogenized or not at equilibrium yet because there's still some business happening here. Actually, it looks like we're about pH 6. Let's add another drop of base here. 1 drop. Oh, that's an acid. Doggone it. Let's add a drop of base here. Well, it's kind of cool. Got a lot of different colors there. So if the acid and base are perfectly balanced, we're going to end up with a green color. Right now, it's looking like pH 8 to me, but it's slowly relaxing. I think we're there at pH 7, folks. We got the acid and the base balanced. I'm going to add another drop of base because we want to go to... We definitely want to go to pH... There it is. There's your pH 10. There's your violet. There's your violet color. Now we're going to start adding hydrochloric acid. It did rainbow for a bit there, John Doe. We're going to start adding some hydrochloric acid, send it back in the other way. Actually, I think that's more of a blue color than a violet right now. So I'm going to say we're at like pH 9. Let me add a bit more base. 1, 2 more drops of base. Get that nice violet. There we go. Look at that beautiful violet. Beautiful violet color. Hey, we're 5 away from 100 in the live. As soon as we get there, we're going to switch over to this experiment over here, which I think you're going to really love. I think you're going to really love that experiment. Very cool. All right. Thank you there, Preston. I appreciate that. Let's start adding some acid here. I'm going to add like, I don't know, 1, 2, 3, 4, 5, 6 drops of acid. Let's see what happens. Thanks there, Mark. Appreciate that. Man, there's quite a bit of base in there. I added 6 drops of acid. And I can just barely see some red here. Looks like most of the acid was neutralized by base. Let's add like 3 more drops. 1, 2, 3 up there at the top. You can see the red growing in. It's going to react with the base that's present. Hey, thanks, Sarah. J Mass, I appreciate that. Sean, thank you. I appreciate the subscription. Very nice. Looks like we're down to like pH 9. Let's add like 1, 2, 3, 4, 5, 6 drops of acid. Come on, baby. Look at that flash. Come on. We got the whole rainbow going on in there. I should do hydrolysis. Like what kind of hydrolysis you thinking, John Doe? Looks like we've got a little bit excess of acid now. Our pH is at 6. You can see the pH scale right here, right? pH 6. Thank you there, N. Appreciate that. INF. Let's add 1, 2, 3 more drops of acid. Maybe I got 4 in there. Yeah, that pH is all the way down to 3 now. Mark, yeah, I'm doing it at home. This is something you can definitely do at home. It's not too bad. Yeah, the universal indicator is a little, it's It's not something you want to drink, but other than that, you're fine. Let's add like 1, 2, 3 more drops of acid. Hey, Clarissa, welcome aboard. All right, we are down at like pH 3. Let's add some base now. Hey, we got over 100 people in here. Give me a thumbs up if you want to move over to this experiment, which is kind of fun. What pH should tap water be at? Your pH tap water should be like somewhere between 6 and 7. Sometimes it drips down to about 5, but you know, anywhere from 6 to a little bit below 8 is going to be fine. Hello there, Oben. Welcome aboard. I'm going to add 1 drop of base here so we can get a flash of the rainbow. Come on, baby. Give me that rainbow. Come on, man. Come on. Give it to me. There it is. Got a little rainbow flash, which is cool. So it looks like Charles wants to try the other experiment. Hello there, Danielle. All right, let's do the other experiment. pH 2, is it drinkable? Yeah, there's a lot of like soda pops and fruit juices that get down close to pH 2. You know, that the pH of something doesn't really tell you a whole lot about whether something's drinkable or not. It's more like the toxicity of the things involved. Hey, Frag. Frag is saying that they, anytime I see someone calling me Mr. White, we have to humor them. So here we go. I don't know if I'm Mr. White, and I'm certainly not Breaking Bad, but it is kind of fun to do chemistry experiments for people, I will say that. And one of my favorite colors is blue. All right, back to the experiments. Thank you there, Frag. You got it, John Doe. All right, let's go over to this experiment here. Make sure I've got my, do I got my dyes? Uh-oh, what dyes am I going to use for this? Here we go. I got to get my dyes going on here. Oh, yeah. Okay. Let's see. Where's my violet dye? I don't know. Uh-oh. Well, we might just have to try a different color today. That might be fun. Where is it? Let me go back to this just for a bit while I'm looking for my dye here. Let's add a drop of... Here, we'll do this. We're going to turn this off. We're going to add a little bit of base here, and we're going to watch what happens. 1, 2, 3, 4. Let's see what happens after 4 drops. We're going to let that mix for a bit. See what happens. There it is. There's the purple dye. I knew I had it somewhere. It looks like night. Looks like night encroaching on the day, doesn't it? Yeah? A little bit. Hey, thanks there, J-Mass. I'm the one who stirs. That's hilarious. Isn't that beautiful, that a little effect there? Here, let's add a little bit of acid, see what happens, just for the heck of it, up here at the top. All right. Hey, welcome back, Maltoin. How much pH indicators in there? I added maybe, I don't know, 3 milliliters or so of universal indicator. I have to do a chemistry research for my college professor. What topic do you suggest? Frag, this is what I would do. Check out one of my YouTube shorts where I stick a sparkler down in some liquid nitrogen. And there's actually some chemistry that goes on. And I analyze the products. It is a little bit like a summer, a fiery dusk at summer. It's kind of cool. Hello there, Danielle. All right, let's switch over to this experiment just for a bit here, okay? So what I'm going to do in this particular experiment is I have some water in here, okay? So there's water in this bottle. And now to the bottle of water, I'm going to add some alcohol. The alcohol I'm adding is not the type that you drink. If you drink this type, you get really bad intestinal cramps and probably some diarrhea. So it's not real good for you. All right. Let's put it in. Here we go. In goes the isopropyl alcohol. So I'm mixing isopropyl alcohol with water. That's probably good right there. We'll leave it right there. You can kind of see that the two don't look like they're going to mix, right? Can you see like the alcohol is kind of rested on the top? You can see it's kind of bubbly there. And the The water kind of stays on the bottom. To see if they mix, what I'll do is I'll go ahead and I'm going to add a drop of purple food dye. Let's add 1 drop there. See what happens. And look at that, man, that is beautiful. Look at those tendrils. And you can actually see that it kind of stops right in the middle. So there's like 2 layers there. There's a water layer that's down here, and there's an alcohol layer that's up on the top. I think it's gorgeous too, Fredge. Really kind of cool. Yeah, let's zoom in on those tendrils because it is kind of interesting to see. Let me zoom in on them. Let me get this light off for this. We definitely want the light off. Yeah, you can see the 2 layers, right? Can you kind of see the thin line there? And sort of to test, hey, no problem, Tara Chad. To sort of test, I know Bebob. So Bebob is confused. They're saying, hey, wait a minute, Bebob says, water and alcohol separate? Well, we're going to find out. Because the way I did this experiment, there's water on the bottom, and then I poured the alcohol on top, okay? And it does look like they've separated. But to test if they really separate, what we are going to do is we are going to mix these really well. And if they continue to stay separated after, I mix them really well, well, then we know that the 2 do not mix. I have a little trouble with my lights here. Hold on a second. Let's get this one powered up. Just give me a second here. There we go, a little brighter. All right. Let's get that one there. Get this one over here. So once again, I've got water and alcohol in the flask on the right and the bottle on the right. And what I'm going to do is I'm going to mix them to see if the 2 mix. And if they separate, well, then we know that they, if they separate, then we know that the 2 don't mix. So here we go. Remember, alcohol on the top, water on the bottom. We're going to shake this up. Here we go. Shake, 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 shake. We're going to put that right there and see if there's any separation that occurs. I'm going to open this up. I'm going to just put in another drop just to kind of see. So in goes another drop. There's a bunch of bubbles that are obscuring things a little bit. And hey, look at this. This time it looks like the dye is pretty much heading all the way down to the bottom. Yeah, it's going to head all the way down there. So that tells me that the alcohol and the water have mixed. All right? You want to drink that? Listen, man, it ain't that kind of alcohol. It's not the kind you drink. You drink this type and you're going to end up on the toilet for a while. It's going to give you really bad diarrhea. Okay, let's shake that up. So we do see that the alcohol and the water mix. And I just added a little purple dye so we can see things just a little bit better. Okay, now what we're going to do is I'm going to add salt. I'm going to add a bunch of salt to the bottle, okay? I'm not taking a dab, man. I'm telling you. I am not. Isopropanol, Tara Chad. So here we go. I'm going to add the salt to this. So again, what's in here is isopropyl alcohol and water. A bunch of air bubbles. That's why it looks kind of misty. You can kind of see those air bubbles starting to rise. Here, I guess we can just wait and watch that. Watch those air bubbles do their thing. Yeah, look at them up there at the top. It's pretty, isn't it? I don't know, simple things, man. Simple things. Okay, so it might be whom. Hello there, Christy. Yep, you might. Okay, now in goes the salt. So we've got water, we've got isopropyl alcohol, and we've got some purple dye, and now in goes the salt, baby. Come on now. Here, I'm going to use a little, let me use a funnel to help me out. Where the heck my funnel go? Now let's just put it in. Here we go. I'm just going to try to put this in as best I can. Here we go. In goes the salt. So I'm adding salt to a mixture of water, isopropyl alcohol, and purple food dye. Once again, I am adding salt to a mixture of isopropyl alcohol, water, and food dye. The food dye is violet. And then I'm going to shake this up. We're going to watch what happens, okay? One more time. Adding salt to a mixture of water, isopropyl alcohol, and purple food dye. It's going to take a little bit for that salt to dissolve. So let me get this thing shaked up here so it dissolves. All right, shake that baby up. We got to get that. Look at that. Just that's like a cloud of salt. Will the salt bind to the water more than the alcohol? Well, Lance, looks like Lance might have some experience with chemistry. Yes, indeed. The salt dissolves into both, but the salt really binds strongly with the water. They form what are called ion dipole forces that are quite strong. And in fact, the salt ions, the sodium ions and the chloride ions in the salt, they attract the water molecules really strongly. And I like to make this analogy. Just like when two people are attracted to each other very strongly, they sometimes fall in love and then date exclusively. The same thing right now is happening to the water and the salt. The water and the salt attract so much that they start to mix exclusively and they will exclude the alcohol. Let's see if it's going to work. It's totally working, I can tell. Come on, baby, it's totally working. Do you see it? Do you see it? Look down there at the bottom. Look, tell me what you see down there at the bottom. I don't know about you, but I'm seeing like on the bottom it's blue. Yeah. On the top, it's like a pinkish. And in the middle, it's more violet. It's crazy, right? So what's happening here, once again, is the salt and the water, they mix really strongly, and they date each other exclusively, so to speak. It pushes the alcohol out. Now, it doesn't happen immediately. So in the middle, there's a mixture of the water and the alcohol. Mixture of the salt water and the alcohol. You can see the three layers. So you got the salt water layer, you got the alcohol layer, and you have this mixture of salt water and alcohol. We call this an emulsion. It's a transient mixture. It doesn't last forever, and you can tell it's shrinking with time. And what is cool is the purple dye that I added, you can tell now, is made of two different dyes. One of the dyes is blue, and the other dye is like a pinkish color. And we can tell that the blue dye dissolves better in the saltwater layer, and the pinkish dye dissolves better in the alcohol layer. Isn't that beautiful? Molecules we can't see, and yet we can control them. You got it, John Doe. I think I want to color this just a bit more. So I'm going to add 2 more drops. Maybe, yeah, 2 more drops. We'll go 2 more drops of the food dye. There's 1. And it goes, look at that. And come on, that's beautiful. And look at how that food dye, you can tell it's more dense than the alcohol layer, but it's less dense than the saltwater layer. So it floats. It looks like a pill bottle. You're right. It floats on the saltwater layer. Now we're going to mix it and see what happens, okay? I think we can use 1 more drop. Let's see that again. I want to zoom in on that because that really looked kind of gorgeous. Here we go. Let's zoom in. Okay, I'm going to add 1 more drop of food dye. You can watch it happen here. And then we're going to mix it up once more. Boop, there it goes. Really pretty. Really pretty. Thank you there, Lance. I appreciate that. Thank you there, Dag. Appreciate that. Lots of fun that we're having. Okay, let's mix this baby up. Thank you there, Christy. I think it's pretty too. It's like science and art together. Let's give this a shake. Zoom in more. All right, Q, you got it. Q wants me to zoom in more before I mix. There you go. Take a quick look. So, and Celia, I apologize, I'm not saying that. Thanks, Bill Nye, that's funny. So, what's going on here is I have a mixture that contains salt water, that's here on the bottom, alcohol, that's up here on the top, and violet food dye. So, it's salt water on the bottom, alcohol on the top, and I've just added some violet food dye to it. We're going to shake this up. So, here we go. Thank you there, Q. Hello there, Kimberly. TRV, I won't be drinking it. Isopropyl alcohol would give you some really bad diarrhea. I don't want any part of that. Plus, the salt in there is enough to give me high blood pressure. Kimberly, welcome. I think I do remember you. Give me just a little bit of a reminder. Anyway, In this mixture, the salt and the water like each other so much that I like to say by analogy, they date each other exclusively. So the water and the salt end up in this lower layer. They exclude the alcohol, which ends up in this layer up here. In between, there's a transient mixture. You know, when you shake it up, you mix everything. That makes a mixture of salt water and alcohol. That doesn't last because what's happening here is the salt and the water are finding each other and they're coalescing and coming down here and they're pushing the alcohol out. The violet dye, the purple dye, is made of two different dyes, one of which is blue and ends up in the saltwater layer, one of which is pink, and that one ends up in the alcohol layer. Isn't that cool? Thank you there, Ansi. I appreciate that. Thank you there, at least. Yeah. And some people, you know, seem to really enjoy these colors. I kind of like them myself. I think they're pretty cool. So thanks for joining in the live here. And Chad, it sounds like Chad has tasted some isopropyl. Let's go over here to this flask over here. I want to play around with this one for a bit. All right, so we're going to get this thing spinning. Looks like there's quite a bit of acid down there in the bottom. This has got pH indicator in it. Yeah, look at that, man. Look at that. Hey, thanks there, Grace. Tell your daughter I'm glad they're aboard. Christy, the effect of water repelling alcohol is more an electric effect than a magnetic one, okay? Quite a bit of salt, Christian. So what I did is I used 240 milliliters of water. It ends up being about 280 milliliters of 91% isopropyl alcohol. And then to that mixture, you're going to add about 60 grams of salt and shake like crazy. Hey, all right, this just in. My holiday break's going great. I hope yours is too. Thank you there, Low Key. Oh, nice. Nice. Thank you there, Kimberly. Thanks for joining in, J-Mass. What am I currently teaching in my class? Future Farm. We are on break, baby. So I'm going to add some base to this right now. We're going to add some base here. Let me get the light turned on. So down here you can see the pH scale. So we can tell that the pH is pH 6. It's yellow color. I'm going to add some base to this. So in goes the base. In goes the base. And you can see when I add the base, the pH goes up. Can I put color drops in the green thing? I just did it. Yeah. There you go. I like it, Christy. All right. Now what I'm going to do is I'm going to add some dry ice to this, okay? So remember, I've made this basic. So this is alkaline. In the United States, we use the term alkaline and basic synonymously. Thank you there, Q. Now what I'm going to do is I'm going to add some dry ice to this, okay? Dry ice is carbon dioxide. And carbon dioxide, well, let's just see what it does first, all right? I don't want to tell you what it's going to do. We just want to do it. All right, here's my dry ice. There we go. I got a piece of dry ice right here. By the way, I need to thank everybody who's been joining in my lives. Here's the dry ice. So last week, we did a live. I did some liquid nitrogen experiments. And I happened to post a snippet from my live as one of my YouTube shorts. And it went viral. You can check it out, man. It's like got over 1 million views in just a couple days. So thank you, everyone, to join in the live last time. And just want everyone to know we went viral. So check out my YouTube shorts. You can see where I put an LED and some liquid nitrogen. We did that last week. So here we go. In goes the dry ice. Remember, this is basic. It's like pH 9 or 10. In goes the dry ice. It's bubbling around like crazy, baby. Come on, man. Look at all that cloudiness. And whoa, look at that color shift. Come on, man. We went from like a violet color. We are now at green. That's neutral. So the carbon dioxide has neutralized the water, and now it's made it go acidic. That's pH 6. Isn't that cool? So yeah, carbon dioxide is indeed an acid. When it dissolves in water, it makes the water go acidic, and it also neutralizes the base. So here, I'll show you. I'll just squirt a bunch of base in, okay? So we're going to squirt a bunch of base in, sodium hydroxide base. Here it goes. Big old squirt. See, it goes violet. And as the carbon dioxide bubbles through, I may have given it too big of a squirt. We're going to find out. You got it there, Starborn. We're making some sparkling water. Thank you there, Carolina. Carbonic acid is your favorite. That's cool. CO2 equals acid. In theory, this is what soda does to your stomach. Well, yeah, a little bit, but you're not getting this much carbon dioxide in your stomach. Uh-oh, I think the color's shifting. I think that color's shifting just a bit. We're down to like a pH of 8 now. Here it goes. Carbon dioxide still bubbling through. When that gets green, the carbon dioxide will have neutralized our system. Thank you there, Kimberly. There we go. It's neutral. We are at neutral. Are clouds in the sky really human-made? Magic. Well, the ones made by planes are. But most of it, no. That ice is working hard, Q. You got it. And now I think we're a little bit below pH 7. You can see it's like a yellow-green instead of just a green. We're below pH 7 now. Don't serve this at the Christmas party. Funny. So, yeah, the carbon dioxide has indeed neutralized the base that I added. In the stomach, does this in reverse. The hydrochloric acid catalyzes decomposition of carbon dioxide into CO2 gas, hence the burps. No, this is not Gatorade. This is definitely not Gatorade. You need me to be your chemistry teacher. I'd love to be your chemistry teacher. Does dry ice usually sink? Yes, it's more dense than water. Dip a finger in it, hoodie? Sure, here we go. And it goes, right? And no big deal. The pH in your stomach is already way lower than this. True. How long will it go if you add more dry ice? It goes until all of that turns into a gas. So that dry ice, we say it sublimes. Here, let's zoom in on it. It's kind of neat to see. It's a little... So I'm going to turn the spinner off. There we go. There we go. So there's that. It just looks like it shimmers around it, doesn't it? So it's like this shimmering film. And if you're paying close attention, I want you to think about this. I want you to look at those bubbles. So look at those bubbles that are coming off the dry ice. It's easier to see in slow-mo, but you can still see it. My question for you is there a cloud already inside the bubbles when those bubbles are in the water? Or are those are those bubbles kind of transparent? If you look closely enough, you can indeed tell that the cloud is already inside the bubble when it's in the water. You can see it. They're cloudy. And so the cloud that you see at the top has already formed inside the bubble before they get to the top and pop. So there's a misconception. A lot of people think that the cloud that you see at the top comes because there's cold carbon dioxide gas up here that's causing water vapor to condense on it. And that's not what's going on. If you look very carefully, you can see that the cloud is already inside the bubble. So when these bubbles are made, somehow water evaporates into the bubble and condenses into clouds. So the cloud's already in the bubble. Isn't that cool? Yeah, it's dry. Dry ice is dry. Let's add a few drops of base here and see if we can watch that dry ice neutralize the base. Here we go. We're going to let's add like 1 drop of base. There it goes. You can see it go blue and it's green. There it goes. So why is it cloudy? So Terra cloud, the reason why it's cloudy is when the bubble first forms, all that's in there is carbon dioxide. That should make sense. But water has a vapor pressure, so some of it will evaporate into the carbon dioxide bubble. But as soon as it does that, that gas is so stinking cold in there that it just condenses. So all of that water that ends up evaporating into the bubble condenses immediately. Yeah, Bob, sorry. Yeah, I'm going to add 2 drops of base. Here we go. 1, 2. I should probably tell people what I'm doing here because it does look like magic if I'm not talking about it. You got it, Tara Chad. Vapor pressure. You're right. So John Doe, if you try this experiment in glycerin, glycerin has a very low vapor pressure. So if you try, putting dry ice in glycerin, what actually happens is, the bubbles that are formed there are transparent. There's no cloud in them because of the low vapor pressure. Isn't that cool? Absolutely, Kimberly. Kelsum, chemtrails, I want to make sure I understand what you mean when you say chemtrails. Thank you there, Future Farm, before I answer. Is there any vaporized carbonic acid in that cloud? So Katara. Carbonic acid does not exist in solution, just so you know, but it does exist in the gas phase. My sense is there probably is some gas phase carbonic acid in those bubbles. I'd love to have you. Yeah, there you go. Thank you there, Bob. Thanks for your service. Yep, contrails, condensed water vapor. That's exactly what those, lines are that follow a plane. It's well-known physics. It's just water that's coming out, hitting cold air, and condensing. That's right, Future. All right, Kimberly, thanks for joining in. Great having you around. Great having you around today. We had a good time. Definitely had a good time. If there's nowhere for the bubbles to escape, what would happen? I apologize, I'm not sure. Well, I mean, that looks kind of weird. You can just see the bubbles just coming off of that little piece of dry ice that's sticking up in the air. That looks kind of funny. That's true there, Fridge. There's going to be some CO2 in those contrails for sure. Yep, build up pressure. Let's do this. Do I have my CO2 pump machine down here? I do. Let's do some bubble experiments. I mean, people are wanting to do stuff with carbon dioxide, so let's do a little bit here, okay? So we're going to do some bubble experiments with carbon dioxide. Let me get this off of here. Let's get my SodaStream machine. Let's do some bubble experiments, okay, with my SodaStream machine. I've been working on a video. It's going to come out, I'd say around New Year's. I got a video coming out where I explore the physics and chemistry of bubbles. So we're going to use my SodaStream machine here. And we are going to carbonate. We are going to carbonate some water, okay? So I got my SodaStream machine here. You can see it right there. Do ideal gas laws relate more to physics or chemistry? There's a very blurred line between physics and chemistry. So it's taught in both classes. So it's both. Here we go. I'm going to take this water here. We're going to put some carbon dioxide into this. Yeah. And we're going to do some experiments with the resulting carbonated water. So the pressure of carbon dioxide is going to be building up in this bottle quite a bit. Let's take it out. All right, I'm going to put the lid on. I'm going to shake this up because that helps the CO2 dissolve in the water a little bit better. And then let's do some experiments with this, okay? I'll give you a preview of a long-form video I've been working on. Let me get my glasses over here. This will be a little bit fun. Okay. Where's my other glass? I got one more here. Okay. Got my SodaStream machine. I got this glass here, and I've got this glass here. Okay. So these glasses are slightly different, and we're going to explore the differences between them. All right, here we go. So we're going to talk about bubble formation in glasses. So this glass here, let's see if I get a black background so you can see it. I guess I can use my shirt. Okay, this glass here is a special glass. It has nucleation sites etched on the bottom. Let me show you this. Hold on, so you can just see it. Can you sort of see down there? You see that spiral down there at the bottom? You see it? It's a little hard to see because there you go. There I can see it. You see that spiral down there at the bottom? So what they do is they use a laser, and that laser etches little imperfections into the glass. So there's little crevices and pits in this glass. This one over here, this glass over here, is just a normal glass, just a normal everyday glass. And what we're going to do is we're going to pour a little bit of water that's been carbonated into both of these glasses. Remember, this one over here has the nucleation sites etched into it, the one on the left, and the one on the right does not have those nucleation sites etched into them. This is going to work better with a black background. Let's see if I got a black. Well, curses. I can try this. Here, we just switch it over here real quick. We'll just do this. Move it over here. Move it over here real quick. We'll get this set up. So I want to get the background set just right so we can see it. There we go, baby. We're going to be able to see this real well now. Okay. And remember, the glass on the left has the nucleation sites etched into it. The glass on the right does not have nucleation sites etched into it. We're going to see the difference. Here we go. I opened up my bottle. In goes this one. And in goes this one. Let's see if there's a difference. Okay. There we go. All right, let's look real close here. You can see the bubbles coming up from the nucleation sites on this side. Yeah, you see the train of bubbles. You get down just a little bit further. Works better with champagne. There we go. So this is the glass with the nucleation sites in it. And this is the glass that doesn't have the nucleation sites in it. Now this still has, there still will be etches and imperfections in a normal glass. There will, but I think it's pretty clear that we're seeing more bubbles on the site with the nucleation sites than the one that doesn't have it. Fridge, I'm just using my regular old cell phone camera, with good lighting. Now, this is kind of fun, too. What's interesting is most of the carbon dioxide, this is an experiment I did in the video. I've got a long-form video coming out on this. It should be out in like a week or two. We'll see. I want to do it for like, champagne and New Year's and all that stuff. So I wonder if a bubble counts as a nucleation site or a salt crystal or a speck of dirt. So Tara Chad, in the video, I describe exactly what the nucleation sites are. What light am I using for this? It's just a light box. I'm just using a light box. So most of the carbon dioxide, look at this nice bubble we got over here. Look at that. Come on, man. That's just cool. Oh, I popped it. Anyway, most of the carbon dioxide that escapes from a glass is not from the bubbles. It's actually from the surface. So most of the CO2 that's coming out is coming from the surface. Let me show you how I can show you this. And I do this in the video, in my long form video that I got coming out. What we're going to do to show this is we are going to take a birthday candle and we're going to light it. And of course, we know carbon dioxide puts out a flame. So if there's a bunch of carbon dioxide that's coming from the surface, it should put the flame out. Let's find out. Can you see? Oh, yeah, we can see the flame. Good. So there's our flame. All right. We're going to stick it inside this flask here. And look at that, man. It just comes right out. It just goes right out. And that just shows you, it's not these bubbles. There's not very many bubbles coming out here. Most of the carbon dioxide that escapes from a glass of soda is going to escape from the surface. There's an enormous amount that comes from the surface. Let's see how we're doing here with the bubbles now that things have settled down. You can see here in the glass with the nucleation sites, those bubbles are still coming out fast and furious. Well, over here, there's not quite as many of them, are there? So the nucleation sites creates bubbling from the bottom. So yes, what is going on at the nucleation site? There are little crevices in there. So there's little crevices. And I talk about this in the video. You can actually see it going on really well at this site right there. Look at it, it's just firing away like on all cylinders. What happens at the nucleation site is when you pour a fluid into this particular bottle or any glass, the nucleation sites, those pits and crevices, they don't get fully penetrated by the water. And so what happens when the water goes into the glass, those pits and crevices, when the water can't fill them, there are little air pockets there. That's what the nucleation sites are. They're little air pockets. And what happens is the carbon dioxide that's dissolved easily goes into those air bubbles. They're really tiny. And then those little air bubbles, they grow in the little crevice. And when they get big enough, when those air bubbles get big enough, they get buoyant enough, then they detach and rise to the surface. We got another one of those big bubbles on the surface over here. I just want to show you that. Look at that. Isn't that just beautiful? I mean, I just love bubbles and the science of bubbles. So I do have a long form video coming out. Probably not this Monday, but maybe the next Monday. You know, right before New Year's, I got a long form coming out where I'm going to describe the chemistry and physics of bubbles in a long way, and we can easily see. Here's our glass with the nucleation sites, and here's the glass without them. And certainly the glass with the nucleation sites, purposely etched into them, is having more bubbles form. So let's see if I can read through a couple of these. I amended my state immediately. What is the relationship between surface tension and bubbles? Christy, that's a great question. So it works like this. The relationship between surface tension and bubbles works like this. If you have a bubble, we're going to imagine that, you know, this is the bubble, where this is the membrane of the bubble. There's an equation that says the difference in pressure inside the bubble and outside the bubble. We call that delta P. So there's going to be a difference in pressure between the gas on the inside of the bubble and the gas on the outside of the bubble. That has to be equal to the twice the surface tension of the liquid divided by the radius of the bubble. We call that the Laplace equation. And I'm working on a second video that describes the Laplace equation as it relates to bubbles. Beautiful, huh? I love looking at bubbles. Absolutely. Oh, this is kind of fun, too. We can do this experiment, too, just to show you that carbon dioxide is an acid. So here we go. We'll just show you this one as well. So, you know, both of these flasks have water from my tap that I added carbon dioxide to. Let me add to this flask here. Sorry. Not flask, but glass. To this glass, I'll just pour some water from my tap. All right? So this third glass is going to be water from my tap. This is the water that I use to make the soda. All right? We're going to add universal indicator to both of these, and we're going to see what happens, okay? So universal indicator to both of these. And, of course, let's get our pH scale so we can see this. Turn this on so you can see the pH scale a little bit better. Yeah, down there at the bottom. See if we can see that with the light off. Oh, yeah, that looks beautiful. Okay, so water from my tap on the right. Get a little squirt of universal indicator. Looks kind of green. Water from my tap on the left that has carbon dioxide added to it. Remember, I just made soda, so I just used that water on the right, and I carbonated it with a soda stream machine. Come on, baby. Come on, look at that. We got Christmas going on up in here for people to celebrate. Well, come on now. Yeah? There it is. A little Christmas demonstration for those that like to celebrate Christmas. I know not everybody does, but for those that do, there you go. This one's for you if you celebrate Christmas, all right? There you go. So this is water that's been carbonated, and this is the same water. So this is water from my tap. This is the same water that's been carbonated. I like that. That's a cute, cool little Christmas experiment I can do for people around Christmas time. Oh, come on, P3. We need good surgeons, man. I've gone under the knife a couple times, and I tell you what, I love my surgeons. Then what is the pH in the etched glass? Let's find out. All right. If you want to know, let's find out. Come on, let's do it. Here we go. There's my universal indicator. Make an ideal phase, equate engraving, and a testosterone. Is technically mildly alkaline. Okay, here we go. Here we go. Somebody asked, what's the pH in the etched glass? You can see the universal indicator's green, right? But boom! Come on, man. Carbon dioxide makes things really acidic when it dissolves in water. So, yeah, you know, soda water is acidic. Soda water is acidic. All right, at some point, What happens when it goes flat? Well, let's see. Let's try it, okay? So I'm going to make this stuff go flat. I'm not sure this is going to work, but we're going to try it, all right? Here, let's put this one in the middle. Just to give it, it's just like a nice balance, isn't it? Look at that. Look at that. Come on, that just looks like Christmas up in here. Okay, now what we're going to do is we're going to add a little bit of Mentos candy to the flask on this side over here. So this is the same color as this. Here, let's get this out of here because we got a control going on, all right? So we got 2 flasks here. Those are the same color. And now what I'm going to do, I'm going to try to make this one go flat. And I'm going to try to make it go flat. Actually, I'm going to do it with the etch glass. We're going to try to make this go flat by adding Mentos candy. Because what Mentos candy does is it provides nucleation sites. And that, nucleation sites are escape portals for carbon dioxide. And if the carbon dioxide comes out, then, of course, it should be less acidic. So let's take some Mentos candies here. Here we go. You're like, what the heck? This guy's got Mentos candies in his basement? Yeah, it's because I'm doing experiments down here all the time. And I love doing experiments with Coke and Mentos. Anyway, here's the Mentos candies. All right. We're going to pop them into this flask over here because the question was, what happens when the soda goes flat? We're going to try to make this one go flat. Here we go. In goes the Mentos. Look at that fizz. Look at that fizz. You can hear it? Yeah? Love that sound. All right, I'm going to try to shake this around just a little bit to try to get the CO2 to come out a little more. I'm helping it. I'm helping it. And what we should expect to see when enough carbon dioxide comes out is that this should have a slightly more orange tint to it than this one over here. This will have a slightly more orange tint because the carbon dioxide comes out, and that's going to raise the pH slightly. I don't know. What do you think? I think I see it. I actually think I see it. It may be because it's what I want to see. I want to be careful. And if you think I'm full of crap, I want you to let me know. But to my eye, it does indeed look like the flask on the left is slightly more orange than the flask on the right. Give me a thumbs up if you agree, and feel free to give me a thumbs down if you disagree. So user 67 says, I am full of crap. Which may be true. It may be. So John says it looks slightly orange. Vulcan agrees. Daniel says pumpkin and cherry. John Doe giving me a thumbs up. Yeah, I'm thinking it's a little more orange. But again, if you disagree, that's okay, man. I mean, we want to get it right. We want to get it right. We don't care who's right in science. We care about what's right. Maybe just a bit. Yeah, it's a little tough to tell. I wish I had maybe a spectrometer to help me tell a little better. A lot of folks are saying it's a little more orange. Yep. All right, folks, we're getting close. Can I stir the Mentos with something? Sure. Let's stir it a little bit. Hold on a bit. What do I have in here to? Oh, you'd think I'd have something in my lab to stir things with. Well, I just use the. I can just use the. Yeah, I can just use the. No, that's got a little bit of acid on the bottom. I wouldn't want to do that. That's gonna. Here, I'll use a fresh. A fresh dropper. So we'll stir this up just a little more. Give it a stir. Boy, I got some cleaning to do when this is done. Stirring it up. Boy, it's close. To my eye, that's a little more orange. I think it is. But feel free to disagree. So yeah, we're getting close to the end of the live. I've been going about almost an hour, and at an hour, what I'm going to do is I'm going to flip the camera around, and I'm going to talk to you. So if you do not want to see an old man in their basement, now's the time to get out of the live, okay? Fair warning. So great question, ZZ. Beautiful question. Are the Mentos in water alone acidic or basic? That might skew the results. So ZZ, I have done this experiment. You can test it yourself. I have added Mentos to, water, and it does not change the pH. But again, what do you do? What do you want to make it purple? To make it purple, I'd add a bunch of base. Yep, sugar is neutral. So if you read through the ingredients of Mentos, you'll find that everything in there is neutral. I think it's now only as it's thicker. Could be, Bob. Could be, Bob. It just looks brighter, perhaps. Here, let's switch it around to see if it's a lighting effect. So let's just switch the two around to see if it might be a difference in lighting. See if that, no, that still looks more orange to me. Actually, it looks a little bit more dramatic now. I don't know. It's hard to tell. It looks more orange to me. Yeah, it looks just a bit more orange. Just slightly more. I think it's... No, ZZ, don't trust me. Do not trust me. If you ever get the chance to do that experiment, you better make sure you do it. Do not trust in science, right? Don't trust people. Trust the data. I shouldn't say that. Trust nature. What if I did drops on a glass side? That'd be fun. From the top, you got it, Floored. Take the Mentos out. Breezy, good idea. Good idea. All right, here we go. Trust but verify. Don't trust, man. Don't trust people. So here's from the top. That's the one that I did not add Mentos to, and that's the one that I did add Mentos to. Here, let me do it long. Come on, man, from the top. Come on, from the top. You can totally see a difference from the top. And I'm an old man, and I can see that. But again, I could be wrong. Let's switch it this way. Let's switch it that way. Yeah. Yep, different thickness, shapes of glass could play a role. Yep, certainly could. So here, let's do this. Let's do this. Let's do this. Here we go. Put these over here. Do this. Put this here. Put this here. All right. All right. There we go. Pour this in. There's that one. Pour this in. There's that one. I still see a difference, folks. I still see a difference. There's the red. Pour it into that one. There's that from that one. I mean, here's the easiest way to do it. We'll just take both these out, right? We're going to take them out of the screen. I'm gonna put both back in the frame. You don't know which one. You do not know which one's which. We'll pop it back in the frame. And when I pop it back in the frame, you're going to tell me which one looks more red, okay? And you're going to put R if you think the more red one's on the right, and you're going to put L if you think the more red one's on the left. Here we go. In they go. You tell me what you think. What do you think? R. Come on, baby. Look at that. Yeah, you can totally tell the difference. Yep. Look at that. Yep. Absolutely, folks. Okay. All right. There is a visible difference. Come on, man. That's cool. That was fun. All right, man. Let's turn this thing around. Let's talk a little bit. See how folks are doing. All right. Let's flip this baby around. All right. Oh, man. Christy gave me an L. Okay. Christy, I think maybe in this case, L might be for lose. Hey there. Nice, Christy. Hey, the cousin. Great having you with us. I hear you, Peanut butter. Hey, thanks there, ZZ. It's just for fun. Absolutely for fun. Yeah, my son and I were my son and I did the bubble video I'm telling you about. We did that together. So we'll be looking for that in maybe a couple weeks. Just before the New Year's, champagne, New Year's, people drinking champagne. We're going to talk about the science of bubbles. Got a little long form video coming out. We're going to have a good time with that. No, I didn't dye my hair. No. That's my hair. Did get a haircut recently though. Thanks, there, peanut butter. So we were just going right or left, Christy, based on what we were seeing on screen. That's the idea there, Lost. Just for fun. Just for fun. I'm not going to break bad. How you doing there, Lou? Well, hey, come on, look at this. Holy cow. John tells me, love what you do, and I really love science. Wishing you and your family a Merry Christmas. John, Merry Christmas. That's very, very nice of you. It's not necessary, but I do appreciate it. You know, little gifts like this do help me, fund the experiments that I do. I spend probably, I'm gonna say maybe $2,000 to $4,000 a year on the experiments I do, and I make about I make about that on my channel every year. So I just about break even. So these extra gifts that I get are very, very appreciated. There you go, man. I'm breaking good. Breaking happy. I'm breaking happy. Thank you, science nerd. I appreciate that. You too, Lou. I can't do that peanut butter, and I wouldn't want to do it anyway. Could be John Doe. Could be because of the bubbles, but I'm not sure everybody noticed that. I noticed it, but I didn't say anything about it. But yeah, I noticed that the red one had more bubbles. I did. Fixing good. Breaking Bad, fixing good. I like it. Well, I do a hot air balloon experiment. Paulie, we did that one a few years ago. Hey, Terra Chad, that's really nice. Appreciate that. MTZ, yeah, we're almost done with the live. Yeah, Mr. Shawan, I do. Yes, that's right, Vor. Orange still means the pH is maybe like 4 or 5. The red means it was pH 3. So it still was acidic. We didn't get all the carbon dioxide out. Sorry there, Aedim. I think that's Arabic. I apologize. I don't speak or write it. I'm sorry about that. Oh, thanks, Ariane. I appreciate that. Hello there, Dio. Huh. Tell me what you know about those, ZZ, and how to give them. Thanks, Sarah, the cousin, the cuisine, or how. I apologize. I know I'm not saying your name, but Roy. All right, folks. I've been doing this a while. I'm going to head out of here. Been great hanging out with you. Great time. We did some interesting experiments today. And I just want to say thanks to everybody because it has been my dream since I've been a young man to be able to do science experiments for people. And it blows my mind that I do science experiments on YouTube live and people come and watch. And it's wonderful. You give this old man a chance to live out his dream. And that gets harder and harder to do the older you get. So it's not lost on me. I don't take that for granted. So thank you for joining in. Had a great time with you today, and take some time to look at the beauty that's all around you. It's always there. Taking a few breaths, check it out. And if you understand the science behind that beauty, it just makes it all the more beautiful. So thanks for hanging out today, folks. And we're going to see you next time. Had a great time. So long.